Now, before getting into the next topic, divergence and later topic curl and all, okay, we shall have much more idea about vector field and flux, okay, flux of a vector field, okay. So this is a very important concept, so throughout our syllabus, okay. Now look at here, as I told, again we can define a vector field, am I right? How do I, so shall I define vector field like V, x comma y comma z? That may be velocity of our fluid, isn't it? That may be any vector field, okay. Let me take in the most general, okay. What do you mean by that vector field? That vector field may, again, that means this is a vector, I mean, depending on the spatial point, am I right? At different point in space, it takes a different value, isn't it? That's how we defined field, okay. Field is some quantity which takes what you call different values at different point in space, isn't it? Now again, what do you mean by V as a function of x comma y comma z? That means V is equal to Vx into x cap, am I right? This x component depending on x comma y comma z into x cap plus y component. I hope you can find the difference between component and variables. Vx is a function of xyz. Vy is a function of xyz. Are you getting the point? Okay. So x comma y comma z. Y cap plus Vz x comma y comma z into z cap. Am I right? I have written like this. Okay. We define vector field like this. Okay. And to have some mental picture, we draw that one, am I right? By the representative lines, isn't it? We draw vector field by a representative line, isn't it? Is that okay? So there are two ways of drawing that one. As I told, one way is each and every point in space is assigned by a vector, okay? Each and every point in space is assigned by a vector. Suppose like this. These are the point in space, okay? These are assigned by a vector. That's one way of representing that one, am I right? But it's quite difficult, isn't it? How many points you have in space? Infinitely many. You have to draw infinitely many vector, okay? Where length of the vector, okay? So this is the vector field at this point actually. This is the vector. This is the, how to say? So this is the vector at this point. This is the vector at this point. This is the vector at this point, okay? That's how you can draw, am I right? Speak out. If you want to draw any vector here, you should get its magnitude. According to magnitude, you should grab its direction. Okay, according to that, you have to draw one representative arrow, isn't it? Where length of this arrow will talk about its magnitude, direction, isn't it? That's one way of representing that one. That's what I told. Other ways, okay, again, so after doing this kind of representation, okay, so you have done this kind of representation, what you can do is you can make a continuous curve where that curve is tangent to all of these field lines. Okay, you can make this kind of continuous curve actually, isn't it? You can make this kind of continuous curve, okay? So here the vector field strength is defined by its length, am I right? But if you make a continuous curve which is tangent to this field line, okay, then how do you record vector field strength, isn't it? In that representation, how do you record vector field strength? So that vector field strength will be recorded by the density of the field line. If density of the field line is more, that means if field lines are closer together, field lines are closer together, then field strength is more. Strength, magnitude, you have to talk about magnitude also, am I right? So if field lines are far away, if density of the field line is low, then field strength is low. That's how we record the what you call field strength. Is that okay? Here field strength will be recorded by length of the arrow in this representation. There are two representations of the vector field you have seen. Usually we go for this one, okay? We shall see that one. Now look at here. Again, once you refer this one, look at here. In the second representation, I told density of the field line. Am I right? So that's also related to this flux only. We shall see that one. Okay. Now look at here. let me take the simplest case. Okay, let me start with the simplest case, then I will generalize that one. Okay, that's what many books do. Okay, if you see Griffith's electrodynamics, okay, if you read that one, he will start with the simplest case, then he will generalize that one. That's the best way. Is that okay? Because we don't have to spend with mathematical proof most of the cases, isn't it? Only thing is we need to apply them. Okay. Now look at here. I have a uniform vector field. Okay. That means magnitude as well as directions are constant everywhere. Vector field is equal to V naught into some n cap. This n cap direction. Is that okay? Is this uniform? No? Okay. I have a uniform vector field. Is that okay? Constant. Whose magnitude is also constant, direction is also constant. Wherever you take vector field, strength is same, direction is same. Is that okay? Let me take uniform vector field. Okay. Now let me held the what you call area. So like this here. So to this vector field. I hope you can see this a plane. Okay. Let me consider a plane like this. Is that okay? How do I consider like this? Is that okay? Let me consider a plane here. Is that okay? Now that plane, okay, again. Now look at here. That this is an imaginary plane. Okay, this is an imaginary plane. Okay, it's our mental picture here. Okay, imaginary plane. So again, this is plane. Okay, this is not curved surface. This is a planar area. Okay, let me consider one planar area. Okay. Now, again, once I consider this imaginary plane, okay, then again these field lines are passing through that one. Am I right? So can I check? Can I just do it like this? That's the best idea, isn't it? These field lines are passing through that one, isn't it? So can I? Isn't it? So can you imagine that one? So can you imagine now? I hope now it's better. Am I right? These field lines are piercing this surface. Am I right? Let me draw it here. Are you getting a point? These field lines are passing through that area, isn't it? Can you just imagine that one? So this is also imaginary surface. Okay. Now I need number of field lines passing through this area. Let me take the total area A. So this total area, surface area A. Okay. I need number of field lines passing through that area, or I need some proportionality factor which gives number of field lines passing through that area. If again, because these are the representation of a vector field. Am I right? It all depends how many vector field line you draw, isn't it? That's your choice always, isn't it? Are you getting a point? In space, you can't see electric field or magnetic field, isn't it? Yeah. It's your choice how many lines you draw. Okay. Suppose your pencil is sharp, you may draw more number of lines, isn't it? If your pencil is not sharp, you may draw less number of lines, isn't it? So that's why we can only talk about proportionality. Number of how to say, again, we cannot count exact number of field line passing through the area, because field lines are our constructions, isn't it? Our mathematical constructions. Okay. So that's why we can talk about, again, what is that proportional to? What is the quantity that is proportional to number of field line passing through the area. Is that okay? Now let me take two situations here. One situation, so I am going to place my area like this. Is that okay? I am going to place my area like this. Okay. So can you give one pencil? Yes. Suppose these are the field line. Okay. These are the field line. Okay. So I am going to place my surface area like this. Okay. So this is a field line. I am going to place my surface area like this. Is that okay? Now look at here. These field lines are not passing through the surface area, isn't it? These field lines now grazing the surface area. They are not passing through them, isn't it? Have field line like this, have surface area like this, okay? So this surface is parallel to your field line, or your field lines are on the surface actually, isn't it? They are on that one, isn't it? In that case, look at here. If you count what is the number of field lines which are passing through the surface, that is 0 practically, because it is infinitely thin. So it is very, very thin. Is that okay? This thickness is infinitesimal. Is that okay? Yeah, you can take these lines only, isn't it? You can take this. No, I don't want to draw that line. Okay, I need this one later. Okay, now look at here. So, but if I place this one perpendicular to this one, okay, now look at here. Your field lines are piercing that one. Okay, your field lines are passing through this area. Am I right? Are you getting my point? So that's why number of field line passing through this area, that depends on relative orientation of this plane and this field line, isn't it? Relative orientation. Are you getting my point? If your plane is like this, number of field line passing through the area is almost 0. Is that okay? If your plane is perpendicular to this vector field, okay? If your plane is perpendicular to this vector field, then number of field line passing through this area is more. Am I right? Is the maximum value. If you held this plane in some inclined direction other than what you call so perpendicular and parallel, if you held that one in some other inclined direction, then you will have number of field line passing through this one is some intermediate value, isn't it? Now we need to quantify that one, am I right? We need to quantify that number of field line passing through this area, isn't it? Okay, we call that one as flux of vector field. Flux of vector field through that area. Okay, look at it. What I have taken? I have taken vector field also, uniform vector field. I have taken planar area. Okay, later we shall generalize. Okay, that flux, look at here, to quantify that one, we call that one as flux of field line. Okay, that quantity which is proportional to number of field lines passing through this one, we call that one as flux. Flux of field lines. Okay, so through the area. Now look at here. To quantify that one, what we do is we define one vector. Is that okay? Now it is useful. Is that okay? Suppose if you have a plane like this, okay? We define one vector. We call that one as area vector, which is perpendicular to the plane. Can you just imagine? Okay, if you have area, is that okay? If you have area, okay, so area will have what you call, so surface area magnitude is A, okay? We define a vector perpendicular to that area, okay? Suppose if that direction is n cap, okay? So then that vector, whatever we define, area vector, that's equal to whose magnitude is area itself, direction is perpendicular to the surface. Area vector, we are going to define area vector. Okay, we are going to define an area vector, okay, whose magnitude is area itself, okay, whose magnitude is surface area itself, whose direction is perpendicular to that one. Okay, we are going to define that one. Is that okay? Like this. Is that okay? I have a surface area. Okay, so can you see this one? Can you see the pencil? And I have a vector which is perpendicular to that one. Suppose if this area is larger, then this vector magnitude is larger. Magnitude of the vector is area, surface area itself. Okay? Yeah. Now look at here. I'm going to define this flux as dot product between this vector field and this area vector. Now this dot product will quantify number of field line passing through this surface area. Look at here. If that area is perpendicular, if that area is parallel, to the vector field. You have vector field like this, okay? Suppose this is a vector field, okay? You have vector fields like this, okay? But again, your area is parallel, but area vector is perpendicular, isn't it? In that case, our flux or our number of field line passing through this one is 0, isn't it? Now look at here. So if you place your plane like this, okay? If you place your plane like this, your area vector is perpendicular to the plane, isn't it? Okay? But vector fields are what you call so parallel to the plane, isn't it? So angle between them is 90 degree. Can you just imagine? So can you just imagine? Is that okay? Angle between them is 90 degree, isn't it? In that case, flux is 0 or number of field line passing through the surface area is 0, isn't it? Suppose if you held your surface area, okay, like this, or so let me take it like this. Is that okay? Suppose if you are holding your surface area like this, okay? Now, if again your vector field lines are like this, okay? Your vector field lines are like this. So this is your vector field line, okay? And this is your surface area vector. Okay? So in that case, what is the angle between your vector field and this area vector? 0, isn't it? If you take this one as a vector field, okay? Okay? If you take this one as an area, isn't it? The dot product is what you call so cos 0 maximum, isn't it? So that's how this dot product will quantify. Again, because when you place this one perpendicular to, when you place this area perpendicular to the vector field, this area vector will be parallel to the vector field. Parallel or anti-parallel. That's your choice, am I right? That's your choice. You can, again, whenever you have area like this, you can take area vector like this or like this also. So that's your choice, okay? So now what I do is, I'm going to what you call, so take area vector like this, okay? So that area vector is parallel to the what you call vector field, okay? Or when plane is perpendicular to the vector field, okay? Plane is what you call so perpendicular to the vector field, but area, in that case, area vector will be parallel to the vector field. In that case, dot product is maximum or number of field line passing through that area is maximum. Okay, so just search in Google about animation of electric flux. Okay, just watch some animation. Is that okay? Now look at here. See this flux properly. Okay, what is this one? This is proportional to number of vector field lines or number of field lines passing through area A. Is that okay? That is proportional to number of field lines passing through area. Why we have to write proportionality? Because we can't write equality. That all depends, am I right? I may draw 10 field lines, you may draw 20 field line, isn't it? That's all depends, okay? That's the representative lines. So now look at here, number of field line passing through the area A. When area vector is perpendicular to the vector field, so that means you have area parallel to the vector field. In that case, area vector will be what you call so perpendicular to the vector field. In that case, number of field line passing through that one is 0. Dot product is 0. So when your area is held perpendicular to the vector field, your area vector is parallel to the vector field. In that case, you will have what you call maximum dot product. Is that okay? A vector and V vector will have the same direction. Is that okay? Let me just draw this. This is area vector. This is V vector, okay? Have the same direction. Now, here area vector is like this, outward from the board, but V vector direction is here. Okay? 90 degree. That's why dot product vanishes. Is that okay? So, this will quantify number of field lines passing through the area A. Remember, this depends on, okay, magnitude of V. Okay? Magnitude of area vector, that means area itself, okay, as cos of angle between them. Is that okay? Now, if you increase area, then also number of field line passing through that one will increase, am I right? If you decrease area, surface area, then number of field lines passing through that will decrease. It will proportional to area. If you increase field strength, okay? If you increase field strength, you have to draw more number of field line, am I right? If you draw more number of field lines, more number of field lines are passing through the area, isn't it? So that's why if you increase field strength, then also flux will increase, isn't it? Number of field lines passing through the area will increase. And that depends on cos of the angle between area vector and vector field. Okay? If that is 90 degree, it is 0. If that is 0 degree, it is maximum. Is that okay? So now, whenever, yeah, any question here? Speak up. Now, the best way to imagine that one, can you just switch on your torch and give me?
Sir?
Yes.
Sir, the angle is increasing, then what happens?
Angle can be,
From
what you
90
call?
degree.
90 degree, again, it can be maximum 360 degree, am I right? After 90 degree, again, dot product will be negative, but you just think of magnitude. Is that okay? For a time check, think of magnitude. Even if cos theta is negative, again what will happen is, again, your field lines are what you call opposite to this area vector. That is the meaning, am I right? If field lines are opposite to area vector, then you will have negative flux.
So what about the P dot A?
Hmm.
That will basically give us the angle between P and A.
Huh.
That's I think one.
No. What he is saying is, again, if you increase the angle more than 90 degree, then what will happen?
Then of course cos.
No, then so again cos 180 degree, those things can happen, am I right? So if that happens, then flux will be negative. But magnitude of the flux is a measure of number of field line passing through that one, okay? Now look at here, for any area, you got two choice, okay? So you can consider your area vector like this or like this also. Is that okay? You got two choice.
Sir, negative direction means area and...
Area vector is what you call, is making obtuse angle with the vector field. But that magnitude is a measure of number of field line passing through that one. Is that okay? Now, suppose if you end up with this situation, you can just invert your area vector so that you can make it positive. That's your choice. Is that okay? For open surface area, this is open surface area, am I right? Not closed one. You got two choice of considering area vector. One is like this, other is like this, okay? Suppose if you get any negative, if you are worried about that one, just invert that one so that you get flux positive. Or take the magnitude, that everything is same. Is that okay? Yeah, speak out.
Sir, I think it is inward or outward flux, sir.
Wait. For open surface, what is inward, what is outward? You tell. Is that okay? This is an open surface, am I right? This is a plane. What is inward, what is outward? Is that okay? So that's why for open surface area, there is nothing like inward and outward. Only for closed surface area, we define inward and outward. Wait for a while, okay? Here, definitely, the ambiguity. What is the ambiguity? Which direction you have to take? Area vector. That is the ambiguity. That remains here. For open surface area, this ambiguity will remain. Is that okay? Which direction you have to take surface area? Either this direction or opposite to that one. That ambiguity remains as it is, okay? For closed surface area or with reference to something, okay, we will sort this one while working out, okay, in case of your Gauss theorem and Stokes theorem. We shall see that one later, okay. Now, so can you switch on the torch? The best way to imagine this flux is like this, okay. No, I don't have to turn on the light, okay. You can imagine something, okay. Suppose I have a torch here, okay. You can find the torch, okay. You take it as a charge which generates electric field. This torch is the point of charge which generates electric field. Is that okay? Just imagine like this, okay? Now, so this is my area, so this is my surface area. If I'm holding torch like this, okay? So from this torch, what you call your field lines are coming like this. Just imagine like this. Or what you call your light rays are coming like this. So can you just imagine? light rays are coming downward. Okay, if you held this area like this, so then number of these light rays passing through that one or obstructed by that one is more. Am I right? You will get a large shadow below, isn't it? Suppose if you held like this, so then your shadow will diminish, isn't it? So in that case, number of light rays passing through that area will be almost 0, isn't it? Suppose if you have washed your towel, okay? So you have again, so it's around 12 o'clock, okay? If you just dry your towel outside like this, it will dry very quickly, isn't it? Suppose there is no air in the outside. So think like this. Suppose if you dry your towel like this, it will take time, isn't it? So because when you dry your towel like this, okay, then what will happen is more number of this light rays will fall on that one. It will heat up quickly and it will dry out, isn't it? Are you getting my point? So when you have a light source like this, if you held your area like this, okay, more number of light rays are passing through this one. That's why you will get a large shadow below, isn't it? If you had the same area like this, okay, your shadow will diminish. That means these light rays are grazing this one. Am I right? So if you just held your light source like this, okay, like this, these light rays are grazing this area, isn't it? That means they are not passing through; they are grazing that area. In that case, what will happen? So your flux of light rays through this area is almost 0, isn't it? So that's why it depends on orientation of this area, relative orientation of this area and this vector field. I have taken light rays as a vector field here. Is that okay? So that's the best way to imagine that one. So that's why we define, to quantify that one, we define one area vector and that dot product will take care of that one. Is that okay? And that area vector can be either like this or ulta. That's your choice. Okay? If you want to get positive flux, you just manipulate that one. Is that okay? Is that clear? Yeah.
So, sir,
Hmm.
to get flux,
Hmm.
we need some charge.
No, I mean charge will generate electric field. Here I am talking about generalized vector field. Let me first discuss mathematics. Then I will go to charge concept. Is that okay? Yeah.
So that vector fields,
Hmm.
that will generate some, those lines.
Yes.
And those lines.
Vector field is represented by lines. Source will generate vector field. Later we shall see that one. Okay?
So those lines, if they will pass directly to this one,
If they pass through the area, then we count that one. How many number of field line passing through that one. If those are grazing the area, we don't count that one.
so from,
Grazing, I hope you got that one. Yes.
from that we can set the angle between.
So that's why that number of field line passing through that one. So that is quantified by the flux, which is a dot product between vector field and area. Okay. Now in this case, what I did is I have taken uniform vector field. I have taken planar surface area, isn't it? Are you getting my point? Now suppose, let me just manipulate this one. Let me take uniform vector field. But let me take curved surface area. That okay? Let me take uniform vector field but curved surface area. Then how do you count this one? So can you just imagine this one? Can you imagine this one? Vector field is almost uniform, okay? But surface area is curved. So can you imagine this one? Now how do you find the flux? How do you find the flux? Now how do you find the area vector now for this surface which is curved? Speak out. Now what you have to do? area vector will be different. Now look at here. We defined area vector for a plane here, am I right? But this is not a plane, this is a curved surface. You can't define the area vector now, isn't it? So now what we do is, we divide this whole area into small part. Are you getting my point? We divide that area into small part. Is that okay? Again, after dividing that area into small part, infinitesimal small, okay? We define area vector. This is dA vector here. I'll call it as area vector, small area vector. Area vector is always perpendicular to area. This magnitude is equal to this area itself, okay? Direction is perpendicular to this one. I'm going to define this dA vector like this. We are going to divide this whole surface into small patch, so that small patch of area can be practically considered as a plane. And I can define what you call area vector for that. Is that okay? To define area vector, you should have a planar area. So since this is not a plane, this is a curved surface, I divide that one into small patch, so that these small patches can be considered as practically what you call approximated as a plane, and I can define surface area. Is that okay? And then what I have to do is, I have to find dot product of vector field with this dA, isn't it? So here vector field dot dA, vector field dot dA, isn't it? Vector field dot dA, isn't it? So this dA dot product with vector field, it will give what is the flux through this small area, isn't it? This dA dot product with this vector field, this will give flux through this small area. To find flux through the total area, you have to integrate this one. Is that okay? You have to integrate that one throughout this area. Integral with respect to this dA only actually, because this is infinitesimal. Is that okay? Now flux through that curved surface area. Okay. Now let me define this surface as S. Okay. Let me define it like this. We call this as surface integral. Can you imagine this one?
Sir?
If surface is curved, wait a second. If surface is curved, okay, then we can do like this. So we have one more situation. Okay, we have one more situation. Suppose surface is planar. Okay, surface is planar, but our vector field is not uniform. Is that okay? Is that okay? Suppose vector field is non-uniform. Then also you end up with the trouble, am I right? You can't take one dot product. You can consider its area vector, but you can't take one dot product, isn't it? Because this takes different direction at different point, isn't it? Then also what you have to do is, you have to divide this what you call area into small patch. You have to consider dA here. You have to consider dA here. dA here. You have to consider dA here. You have to take dot product at each and every point. Then you have to integrate. Again the same expression. You have to take dot product of dA vector with V vector and you have to integrate. Here I have taken vector field uniform, surface curved, okay? Here I have taken surface planar, vector field non-uniform. Maybe vector field also non-uniform, surface may be also curved, isn't it? Then, in all cases, this integral will give you the flux through the surface area, okay? So that's why, in the most general case, okay? Flux through the surface area, let me define that surface area as S here, okay? This total surface area, I will give the name. This total surface area, I will give the name. That's equal to V dot dA vector. We have to divide the surface area into small patch, infinitesimal patches, and we have to define a surface area. We have to take a dot product between vector field and that area at each point on the surface, and we have to integrate that one then we call it as flux of the vector field through the surface area. Is that okay? Speak out.
Sir, the area which using direction of area and the curved surface area both are same.
No, that depends on the situation. That's what I'm saying. Now look at here. In this situation, in this part of this area, your area vector is like this. Your vector field direction is like this. In this part, your vector field direction is like this. Area vector is almost along the same direction of vector field, isn't it?
But sir, if I will take the curved area in opposite direction.
So this area, yeah, you can always allow to choose this one dA vector like this. That's your choice.
Then angle is also, sir,
Angle will be different. Again, you may get opposite flux. I mean negative flux. That's it. For a time's sake, choose one of them and proceed. Let me define that one later. Is that okay?
I will take that handedness.
No. No handedness will come here. It will come later. You are talking about Stokes theorem. Wait for a while. There is no handedness, nothing here. Are you getting a point? That's always your choice. You can take dA vector like this or like this. But look at here. Whatever this dot product I have taken, okay, this dot products are taken at each and every point on the surface, okay. This area vector is taken at each and every patches. And dot, again, while taking this dot product at this point, you have to take vector field at that point, dot product with the area vector. Vector field at this point, dot product with the area vector. Am I right? Because vector fields are different here, isn't it? You can just see this one. You can just see this diagram. Am I right? Vector fields dot product with area vector here. Vector field and area vector are almost parallel here. Vector field and area vectors, so they may have different direction here. V vector, area vector, isn't it? You are always free to choose this dA vector opposite. Okay, let me quote on that one. Wait for a while. Okay, I mean that's your choice actually. If you choose all of this dA vector opposite, then your total flux will be negative. You can see, isn't it? Here I have chosen dA vector like this. These are the acute angle. Cos theta will be positive. You got positive flux when you integrate, isn't it? If you take opposite, you will get obtuse angle. All of those dot products are negative. When you integrate, you will get negative. That's it. Okay, but magnitudes remain same. Even though it is negative, magnitude remains same, isn't it? Yeah, speak out.
Sir, if the small area and curved surface area, both directions are different, then why we take curved surface?
Small area.
Small area we choose and the curved surface area, both directions are different. Then sir, why we take curved surface area?
No. What I'm saying, we may end up with different situation, isn't it? Then we should generalize the concept of flux, isn't it?
Then sir, what is the function of curved surface area?
That is one of the situation. That's what I told. You have taken one curved surface area. What is the flux through that curved surface area? That is the question. Why you have taken? To generalize the story. Are you getting my point?
Each and every point, the direction of force will be different.
Vector field direction also may be different. Area vector also may be different.
So for that purpose, we can say the dot product, the projection on the BA of the field. Then we can say the angle between them.
Yeah, again, that angles are different. Definitely, these angles are different at different point.
That's it.
So that's why this whole thing is different. And it is infinitesimal. So can I just write like this? So total flux, that's equal to integral of small flux. Okay, that small flux, let me write it as V dot dA. Is that okay? You can write like this, okay? That's a flux through the area. Let me give you one more small idea here. Then we shall. If you have a planar surface area, okay, like this, okay. So there is an inbuilt ambiguity. What is the direction of dA vector that you need to choose, either like this or reverse, isn't it? But if you have a vector field like this, okay, if you have a vector field like this, but you have closed surface area. Can you just imagine closed surface area? Is that okay? Suppose you have closed surface area, closed one. Okay. If you have any planar surface area, okay, if you have any planar if you have any open surface area like this, okay, it need not be planar, okay. So then the question comes whether this dA vector should be chosen like this or like this, am I right? Whether dA vector should be chosen like this or like this, am I right? The question comes in which direction dA vector should be chosen, okay. But when you take a closed surface area, then we can talk about dA vector outward from the region, dA vector inward towards that region, am I right? You can just imagine this one. Whenever you have closed surface area, in that case, you can talk about inward and outward. Is it okay? You got two choices here. You can choose that area vector outward. What do you mean by outward? Outward from this region, because this closed surface area, so that will have one volume V, am I right? This closed surface area will constitute a volume, isn't it? Open surface area will not constitute any volume or any region, isn't it? But closed surface area will cover one volume, isn't it? Then you can call this area vector, this choice of area vector outward from the surface. This area vector inward from the surface. This outward and inward are meaningful only when it is closed. Here you can't say this is outward, this is inward. Where is out, where is in, isn't it? But here you can define outward and inward. That outward and inward are meaningful. Outward to the surface, inward to the surface. That is meaningful only when you have closed surface area. What do you mean by outward? Outward from this region. What do you mean by inward? Inward towards this region. Okay. If you take one more patch of area here, dA vector here, isn't it? Inward to that region. Is that okay? So now if you have that kind of what you call closed surface area, if you have that kind of closed surface area, okay, if you have that kind of closed surface area, now suppose again you can consider there is one charge here or something, okay. From that charge your field lines are, or whatever, okay, there is some source here, so that field lines are going like this. Is that okay? Let me take like this. Vector field lines are going like this. There is some source here. That may be source of some water which is flowing outward like this. Okay, in a pond. In a pond, you can take a source of water, or you can take a charge from that electric fields are going outside. Okay, and I have considered one imaginary closed surface area. Okay, imaginary closed surface area. Now look at here. If I take this area vector, this dA vector, look at here. Once you have chosen dA vector like this, okay, if you have chosen dA vector like this outward from the region, okay, throughout this surface you have to take outward only, okay, while doing that integration. Are you getting my point? While doing that integration, so integration of V dot dA vector, okay, flux through some surface area, yes, okay. So now look at it. If that surface area is closed, then we put this symbol here in that integration. That means this surface area is closed. If surface area is open, we don't put this symbol, okay. I hope you can grab that point. Now look at here. If you have taken this dA vector outward from that region, throughout the surface you have to take dA vector outward from that region only, okay. Are you getting my point? Don't take one side outward from the region, other side inward like that, okay. You have to take, while doing the integration throughout the surface area, you have to take only one convention only, okay. Speak out. Now suppose if you have taken dA vector outside like this, okay, dA vector outside so from that region, so then everywhere this dot product, okay, this dot product is positive. Check this out, because they are making acute angle. Speak out. So they are making acute angle. So that if you integrate all of those dot products, then you will get total positive, right? So now we call that one as flux through this area, outward flux through this area. Okay, now look at here. To find outward flux, we have to choose this dA vector outward from this region. Suppose if you have chosen the dA vector inside, you would have got this integral negative, am I right? Because everywhere you will get obtuse angle. Just check that out. So now look at here. We again, there is one convention that we always, if you have a closed area, okay, we always take this outward flux positive, inward flux negative. That is the convention we take. You have a closed surface area. So now you can see here, there is a source here. Field lines are going outward. Am I right? Now again, it is a convention that we always take outward flux positive, inward flux negative. To make outward flux positive, now here outward flux happened, am I right? Outward means outward from this region, because closed surface area forms a region, isn't it? So to make outward flux positive, what we do is we take this area vector outward from the region. Is that okay? If you take this area vector reverse, what will happen is outward flux will become negative. Here outward flux happen. What do you mean by outward flux? So total flux where our field lines are going away from this region, isn't it? This will constitute a region, volume V, isn't it? Field lines are going away from that one, isn't it? Outward flux happened here, isn't it? Now we want to make that outward flux positive, inward flux negative. Suppose if you have some other situation where you have a sink here, not source, you have a sink here, suppose negative charge, where electric field lines are comes here, isn't it? You know that one. So then you have a closed surface area. Is that okay? So then your field lines are going like this. Suppose so inside a pond you have one small sink where waters are drawn and it is going somewhere. Suppose. Is that okay? In that case, waters will go like this, isn't it? We call this as inward flux. Okay, we want to make this kind of flux, inward flux. So through the closed surface area, negative. We want to make this outward flux positive. That's why what we do is, whenever we have a closed surface area, we always choose our dA vector outward from the region. Look at here. If you have chosen dA vector outward from the region, all of these are obtuse angles between dA vector and vector field. Is that okay? Dot products are negative. When you add all of those dot products, speak out, you will get total negative. Is that okay? To make outward flux positive, inward flux negative, we stick to one convention. What is that convention? For a closed surface area, we take dA vector outward from the region. Can you remember this one? Is that okay? To make inward flux negative, outward flux positive. That's it. There is no other logic. That's what I'm saying. Yeah.
The bottle is closed. And if those sparks will come from the inside, then this will
outward flux. We say outward flux. Can you imagine? Field lines are going outward. That's why I call that one as outward flux. Field lines are going inside to that region. That's why I call that one as inward flux. Am I right? I want to make this flux through this area, in this situation, negative. I want to make flux through this area, closed surface area, in this situation, positive. Isn't it? In this situation, you could have chosen all of this dA opposite. Am I right? In this situation, you could have chosen all of this dA opposite. Am I right? You got two choices for dA vector. Among them, for a closed surface area, we always choose dA vector outward from the region to make outward flux positive, inward flux negative. Just write down that one. Okay? In case of closed surface area, case of closed surface area, to make outward flux positive and inward flux negative, to make outward flux positive and inward flux negative, we choose dA vector, outward from the region of the closed area, outward from the region of the closed volume, outward from the region of the closed volume. Is that okay? This is a closed volume, this is a region. We choose dA vector outward. Is that okay? That's the convention. So try to grab these points, think over it. I think in the evening I will give the best idea about divergence. Now look at here. You have a vector field, okay? What I do is I will take very infinitely small closed surface area. Or I do like this. Okay, I'll take closed surface integral. We call this as closed surface integral, okay? Vector field dot dA, okay? So over some volume V, okay? And I will divide that one by volume. This is flux, okay? Dividing this flux by volume. What is that one? Flux density. Can I say like this? Okay? Flux density. And limit volume tends to 0. This is small v, this is capital V. Is that okay? This is vector field, this is volume. Okay? Limit, that volume tends to 0. I have to diminish that volume. Okay? So that is nothing but divergence of vector field. This is the basic definition of divergence of vector field. What is this one? Volume density actually. This is the density of flux. When you make that volume very small, that will become density at that point, isn't it? So because this is a point operation actually. When you take limit v tends to 0, you are talking about a point. You have taken the divergence at that point. So this is a scalar, okay? This total thing is flux, okay? That's why divergence have got one more definition. It is a volume density of the outward flux. This whole thing is outward flux, isn't it? If this is negative, field lines are going inward. That's it. That's the meaning, okay? So this is an outward flux actually. We say outward flux. If value is positive, that is field lines are actually going outward. If this value is negative, field lines are going inward. That's it. That's the convention, okay? So this is volume density of the outward. Now this is not actually density. How do you define density? Density is a point variable. You know that one? Density is a point variable. Mass density. You can define mass density at different point. Am I right? So to make this one as a point variable, this density as a point variable, I put limit v tends to 0. I will make that volume very, very, very small. Okay. I have a vector field here. Okay. I'll take infinitesimal volume. Okay. And I'll find outward flux from that volume, and I'll divide that volume or flux density, volume density of the outward flux at that point of interest. Okay. That is equal to divergence of the vector field. Okay. Let me define it in the next class. Okay. This is very important idea. This is a basic definition of divergence. Let me define what is this del dot v. Okay, it looks like we shall have to define del operator. Okay, we shall see. I mean, if you take why you are not getting this limit? Tell me. Volume tends to 0 means you have to minimize that volume. Usually, while finding outward flux, I have taken very big surface area. Am I right? Minimize this one, shrink this one to infinitesimal volume. take one infinitesimal volume. Take one surface whose volume is infinitesimal. Find the outward flux density. That is nothing but divergence.
So that infinitesimal volume, then it will be seen to point like point.
Again, it is not exactly point. It is tending to a point. That's what we do in calculus. Am I right? Limit. Is that okay? It is infinitesimal volume. Yeah.
Answer this 1 upon V in the right hand side, sir. 1 upon V.
This will make it flux. This is flux. Am I right? This is flux through the volume. Divide by volume. That's a flux density.
That is the density, sir. Flux upon volume, that is the density.
That's the density. Is that okay? Limit volume tends to 0. Volume and vector field, okay? Don't get confusion, okay? Volume tends to 0. 1 by V into flux through that volume, okay? Flux through that closed surface area, which is, that surface area is constructing that volume, okay? We don't write V here, okay? We write yes actually, okay? We don't write V here. In case of surface integral, we don't write volume, okay? We write yes actually. But for our comfort, yes, comma V. Let me write like this, okay? Surface area, closed surface, closed integral, okay? Closed integral, closed surface area, okay? So that's why one of the definition of divergence of a vector field is it is a scalar. Obviously, this whole flux density is a scalar. Am I right? It is a volume density of outward flux, okay? And that density is a point variable, am I right? You can talk about that volume density of outward flux at different point, am I right? This is a point operation, this is a point variable, and that's a scalar. We shall see what is the divergence later, okay? Yeah. So try to watch some animations in YouTube regarding that flux and all. Get clear-cut idea, okay? Later I will not talk about these things, okay? Is that okay? When I take something directly, if you have that idea, problems will be very easy, okay? Speak out. So if I define the divergence like this, it is very easy to link that one with Gauss theorem, Gauss divergence theorem. We shall see that. If you take volume integral, you will get total flux through the total surface area. It's very easy to link that one to Gauss theorem, okay? That's one of the definition. So in the evening, I will come out with a, what you call, this is related to some integration, am I right? But these are differentiations, am I right? Just like gradient, this divergence is a kind of differentiation. Those are point operation. You can define divergence at a point in space, okay? We shall see what is this differentiation, how it defines outward flux and all, okay? We shall see that.
Sir?
Yeah.
Sir?
Yes.
Sir, so sir, in nutshell, in a statement we can say that divergence of a vector field equals to the flux upon volume, sir. Flux of the closed surface upon volume.
Density. I mean, to make density, suppose how do you define mass density of any substance? Okay, that mass density can be written like this. Okay, suppose if you have a metal block, okay, if your mass is uniformly distributed, you can write total mass by total volume as a density. Am I right? Suppose if it is non-uniform, then what will you do? If masses are non-uniform, you have to take dm by dv, isn't it? Isn't it? And that density may vary, isn't it? If mass is non-uniform, that density may vary, am I right? So this is what I was trying to write here by taking that limit. Is that okay?
Okay, sir.
By taking that limit, I want to write similar thing, density, that is a mass density here. Here it is a density of the flux. Is that okay? And that density can be, again, if mass is uniform, you can write total mass by total volume, or you can take small mass by small volume, am I right? If mass is uniform. But if mass is non-uniform, you have to define rho by dm by dv. You have to take small mass, small volume, you have to take the ratio that may be different at different point of that metal slab, isn't it? Then rho will be a point variable, isn't it? It takes different value at different point. Like that, this is a scalar field. It takes different value at different point.